All right, today we're going to dive into a really neat, surprisingly simple statistical tool called the Binomial Test. It's designed to answer a question that I bet you've asked yourself 1,000 times without even realizing it. You know that feeling, right? Maybe you flip a coin 10 times and it comes up heads 7 times, and you get that little thought, is this coin rigged or is that just luck? Well, is it just random chance or is something actually going on? The binomial test is the tool that gives us a real statistical answer to that exact question. So here's the key. The test is perfect for situations where you only have two possible outcomes. Think pass or fail, yes or no, heads or tails. It helps us figure out if a small group, our sample, is truly different from the larger group it came from, what we call the population. Now, before we can actually use the test, we need to frame our question in a very specific way. And in statistics, that means setting up two competing ideas, the null versus the alternative hypothesis. The best way to think about this is like a courtroom drama. Seriously, you always start with a default assumption. In court, that's innocent until proven guilty. And then you have the new claim that someone wants to investigate, the prosecutor trying to prove guilt. In statistics, we call these the null hypothesis and the alternative hypothesis. The null hypothesis is kind of our boring default position. It basically says nothing interesting is happening here. It claims the ratio we see in our small sample is pretty much what we'd expect, but the alternative hypothesis, that's the exciting one. It's our new claim, arguing, no, wait a minute, this difference is real. It's not just random chance. The test just helps us decide which of these two stories the data really supports. Okay, enough theory. Let's make this concrete. We're going to look at a real-world example involving some students at a place we'll call University XY. So here's our scenario. We know for a fact that across the entire business program, 55% of the students are female. But then we look at one small marketing class of just 10 students, and we see that 7 of them are female. That's 70%. So the question is that a big enough deal? Is this class genuinely different? Or could a 7 out of 10 split happen pretty easily just by random chance, even in a program that's 55% female? Here's the raw data from that very class. We can see the 10 students, and yep, if we count them up, we confirm it, 7 females, 3 males. This is the exact results we're going to put to the test. To actually run the binomial test, we only need these 3 little pieces of information. Our sample size is 10. The number of successes, and that's just a label for what we're counting, in this case, female students, is 7, and the probability we expect to see, based on the whole program, is 55%, or 0.55. Now, with those 3 numbers, a statistical calculator can do its thing and give us one single, decisive number that will answer our question once and for all. And that number is called the p-value. And here it is. For our student example, the calculated p-value is 0.528. This little number is the key to our whole investigation. So what does it actually mean? This is where it all comes together. We have our results, and now we just need to interpret it to make the final call. The rule for figuring this out is super simple. We take our p-value and compare it to a preset threshold called the significance level. It's almost always set at 0.05, or 5%. Think of it like a limbo bar. If our p-value is low enough to get under that bar, our result is significant. If it's too high, it's not. And when we put our numbers side by side, it's not even close, is it? Our p-value of 0.528 is much, much larger than that significance level of 0.05. It's not even in the same ballpark. Because our p-value is so high, the result is officially not statistically significant. And what that means is we don't have enough evidence to throw out our default assumption. We can't reject the null hypothesis. So what's the final verdict here? We have to conclude that seeing 7 female students in a class of 10 isn't really that unusual or surprising, especially given that the whole program is 55% female. The difference we spotted is very, very likely just due to random chance. It's the statistical equivalent of a shrug. And that's the real power of the binomial test, isn't it? It gives you a framework to move past just a gut feeling and actually use data to separate a real pattern from what's probably just random noise. So the next time you see some surprising result, you can ask the right question. Is this really meaningful, or is it just a coincidence?